Hello Lamai. Today we are going to discuss about spontaneity of chemical reactions. Right. First of all, let's discuss what this spontaneity means and what this spontaneity of chemical reactions means. Right. It is like this, Lamai. The concept is like this. Let's think of a some chemical process or some chemical reaction like NaHCl reaction. Right. So this one NaH reacting with HCl to form the NaCl and H2O, right? So when you are to add the NaOH and the HCl to your reaction vessel at 25 Celsius and 180 A reaction conditions, you know a chemical change would occur and you will produce the NaCl and H2O. So this is an example for a reaction which will occur when reactants are to go together, right? So such a chemical change is referred to as a spontaneous reaction, right? So what is the meaning there? So when the reaction R2 brought together, if a chemical change occurs without supplying energy from the outside, such a process is referred to as a spontaneous process, right? So let's think of another example. At 25 Celsius and 180 M conditions, right? You are adding some NaCl aqueous and some water to your reaction vessel. Do you see any kind of change there? No. At the end as well, the same NaCl aqueous as well as H2O liquid would appear at your reaction vessel. So this means when reactants are to go together, reaction won't occur without supplying energy from the outside. So these things are referred to as non-spontaneous processes. Non-spontaneous process, right? So this is a spontaneous process. Spontaneous process, so one can say a spontaneous reaction. This is a non-spontaneous process or non-spontaneous reaction. But Lamai, if you are to apply some energy from the outside, let's say in the form of electrical energy, you would be able to see some change here. What kind of a change? So you would be able to see this kind of change. NaCl aqueous, right, will convert to some Cl2 gas and some H2 gas, right? So this kind of process will occur, right, by forming NaOH. If you have to apply some energy, if some energy is added, right, in the form of electrolysis, you can do so. This thing would occur, right? Do you remember that process? See, right, non-spontaneous process. But if you are to apply some two terminals and some electricity, there you would see, right, there we would see the liberation of H2 gas from here and some Cl2 gas from here. See, the process is non-spontaneous if you are not to apply any energy from the outside. This process is not occurring if you are to add if you are not adding any energy from the outside, but this process will occur if you apply some energy from the outside. So this is referred to as a non-spontaneous process at 25 Celsius and 1 atm. But if you apply some energy, yes, you can do that. Right? Those kind of things are referred to as non-spontaneous processes. Right? The thing is clear. When reactants are brought together under considering conditions, if an reaction is not occurring, such a reaction is referred to as a non-spontaneous reaction. When reactants are brought together with considering conditions, right? If a reaction occurs, such a reaction is referred to as a spontaneous reaction, right? Okay, that is the meaning of spontaneous and non-spontaneous reactions and the spontaneity of reactions. So with this section, right, we are going to predict whether a reaction will occur or not. That means whether a reaction is spontaneous or non-spontaneous under considering conditions without using reactants and products to come together, without adding the reactants and reactants together, without adding reactants together. Now we are trying to predict whether a reaction will occur or not. Right? So that is what we are supposed to do with this section. Right? Again, without adding the reactants to a vessel, without bringing the reactants together, with some calculations, with this section, we are supposed to predict whether a reaction will occur or not, just merely using the calculations. Right? So that is what we are going to do with this section. Right? Okay. Just go to the first point at your note. Right? It says a process or an example, as an example, a reaction is called as a spontaneous process when the process takes place without having continuous supply energy from the outside of the system. One main goal of thermodynamics is to predict whether a reaction will take place spontaneously when a given set of reactants is brought together. In order to predict this the reaction process occur spontaneously or not, in addition to heat absorbed or released, another factor called entropy must be considered. Right? What that means, it is like this now. For this prediction of reaction, whether it is spontaneous or not, we will come across a term called as Gibbs free energy. Right? A term called as Gibbs free energy. Right? Gibbs free energy. One can say Gibbs free energy or Gibbs free energy change. Right? With the use of this thermodynamic parameter, we are supposed to predict whether a reaction will occur or not. Right? Actually, this Gibbs free energy, that thing is a combination of the enthalpy change and another thermodynamic parameter called as entropy change. Right? The relationship of these two guys, these three things, will be given as delta G is equal to delta H minus T delta S. Right? So with the use of this equation, we are supposed to predict whether a reaction will occur or not. Right? So this is their we ultimately stop our lesson right today. So unit 5 ends with this section, right? Before studying about the delta G, which predicts the spontaneity of the reaction, we need to come across the entropy change, right? We had done learning about the enthalpy change. Now, first let's learn about what this entropy change means, what this entropy and the entropy change means. After learning that, we can combine those two to come up with the parameter delta G, which will ultimately help you to predict whether a reaction will be a spontaneous one or not, right? Okay, right. Let's then start our discussion about the entropy change, right? Let's start with the entropy change, right? First start with the entropy. What this entropy means. Entropy, which will be denoted by capital S. Symbol is capital S. Entropy. Right. Entropy, entropy is a measure of disorder, uncertainty, or one can say a measure of thermal motions of your system. Right? Entropy is a measure of uncertainty, disorder, or thermal motions of your system. Right? Okay, let's discuss this idea. So let's consider some H2O. Consider H2O. So H2O can appear as a solid. H2O ice form appear as a solid form. Or H2O can appear as a liquid, which is referred to as water. H2O liquid. They can move here and there, no? Or H2O can appear as a gas, no? Steam, right? It's a liquid, it's a gas, right? So when it comes to a solid, your thermal motions are very limited. Thermal motions are very limited. But when it comes to a liquid, some motions can be seen with particles, and the thermal motions are greatest with the gaseous state. So we can say the entropy of gaseous state is greatest. Entropy of gaseous state is greatest. Why? Entropy is a measure of thermal motions. Entropy is a measure of thermal motions. So greater the thermal motions of your particles of your system, greater will be the entropy. But here, entropy is the smallest. Right? Thermal motions are very limited. So entropy is the smallest. Right? The idea is clear. So entropy is a measure of thermal motions of your system. Right? So we can say when thermal motions of a system are high, then your entropy is high. This is high. It's a measure of thermal motions of system. Oh, another idea is the randomness and the disorder. Let's consider the situation, the disorder thing. Disorder. Entropy is a measure of disorder. We say when the disorder is high, entropy is high. See, here when it comes to a solid structure, it is considered as an ordered structure. The particles are ordered, right? But when it comes to a gaseous state, the particles are moving here and there. Disorder appears here. Less order, less ordered structure, disordered structure. Here, more ordered structure. So, greater the disorder, greater will be the entropy. Greater the disorder, greater will be the entropy. Lesser the disorder, lesser will be the entropy. Lesser will be the entropy. Right? So, one can say entropy is a measure of disorder as well. Right? Okay. Then the next description of entropy. It can be considered as a measure of randomness. A measure of randomness. So, greater the randomness, we say greater will be the entropy. Greater will be the entropy. Greater randomness, greater will be the entropy. Let's come up with that idea as well. Just like this. Let's say this is kind of a NaCl solid. Kind of a NaCl solid. So you have Na plus particles. Right? You have Na plus particles and Cl minus particles. Na plus particles and Cl minus particles in your NaCl lattice. Black colored ones and blue colored ones. Right? Okay. In the solid state, right? So this is the gaseous state. Right? When you had supplied enough energy, you can break all the bonds between the Na plus and the Cl minus, all the ionic bonds, and you can come up with the gaseous state. So Na plus particles and Cl minus particles are appearing. Gaseous state. So this is all about randomness, right? What this randomness means. So if you were to pick a molecule from this space, if you were to pick a molecule without looking at that, if you are to pick a molecule from this space, except space, right? Let's say with this except space, it is definite you will come up with a black color ball. You will come up with, let's say, the black color things are Cl minus, right? So Na plus or something, black color things are Na plus, right? So you will come up with a Na plus. It is definite. No randomness there. Definitely you will pick the black ball, Na plus. So if you are to pick a ball from the same space there in a gaseous state, so it could be a black ball or it could be a blue ball, because these particles are moving with very high speeds here and there, right? So it could be a black ball which you will pick, or a blue ball as well. It could be a Na plus or Cl minus. It is random. More will be the disorder, more will be the thermal motions. What you pick will be a random particle. It could be Cl minus or Na plus, black or blue, right? So more randomness is there when you are with more thermal motions and more disorder. But here it is definite. Randomness is less. So entropy is a measure of randomness. So randomness is less, that means entropy is less. Greater randomness, that means greater entropy, right? So one can say entropy is a measure of randomness. Same idea comes with the uncertainty as well. Greater the uncertainty, that means greater the randomness, entropy is high. Entropy is high. It's a measure of uncertainty as well. Right? Not certain whether you are to pick the black or blue balls, but it is very certain that you will get a black ball with this space. Right? That is the idea. So the things are clear. So you can change the solid state to liquid state and to the gas state with a change of temperature, increase in temperature, as well as change in the pressure. So definitely one can say entropy will be affected by temperature as well as pressure. Right? Okay, we'll discuss a few other factors as well which will affect the entropy. But at the first glance, you can clearly see the entropy will be affected by change in pressure and temperature, right? And entropy will be affected by change in the physical state as well, right? So entropy of a solid is less than the entropy of a liquid, which are very less values compared to entropy of a gas. So physical state also matters for the entropy. Right now? Okay. Right, let's go to the note, Lama Idea. Are you clear with the stuff appearing in the note? It says entropy, capital S, is a measure of disorder, randomness, or one can say thermal motion of particles of a system. Right, when disorder is high, entropy is high. When the randomness is high, entropy is high. You can write it as when the thermal motions of the particles is high, entropy is high. Right? Okay, that picture is also there. The things are clear. Right. Okay. Right. Then let's discuss about the unit of entropy. That is also written. Unit of entropy. Right. When it comes to units of entropy, normally we consider the entropy as a molar entropy, right? Units of, let's consider molar entropy. So units of molar entropy is going to be joules per Kelvin per mole. Right? It is the units of molar entropy. Just correct that thing, right? It should be not the entropy, it should be molar entropy. Do that correction with your right? Units of molar entropy is joules per Kelvin per mole. Right? It's clear? Right. Okay. Let's discuss about the factors which will affect the entropy. Right? So, 3 factors have been discussed already, right? Let's discuss the factors one by one again. Right? The factors affect the entropy. Right? Factors affecting the entropy, or entropy depends on, right? Factors right. The first one is the temperature. Temperature. Actually, temperature means the kinetic energy, right? Temperature means the kinetic energy. So when the temperature is high, more will be the kinetic energy. That means more will be the thermal motions of particles. So when the temperature is high, entropy is high. Simple as that. Right? When temperature is high, entropy is high. Right? You can think of thermal motions to decide that thing. Right? The second factor is the pressure. right? Pressure will affect the entropy. So when pressure is high, we can say the entropy is low. Right? So we can think of a solid liquid gas situation here. When the pressure increases, right, particles will be restricted to smaller volume, smaller space, right? So that concentration will be high. That means you have more particles in unit volume, So distances between the particles are very minimal. That means it looks like a solid. So with solids, the entropy is low. Right? So when the pressure is high, entropy is low. Right? You can think of solid liquid gas situation here. When you increase the pressure, right, you are restricting the same number of particles to a lesser volume, right? So intermolecular distance between the particles are low. That is, looks like a solid. The concentration is high, right? The volume factor, right? The volume factor. Same effect, Laman. Same effect. When the volume is high, right, that means now if you are considering same amount of gas molecules, if you are considering about same amount of molecules with a lower volume as well as with a higher volume, when it comes to higher volume situation, you have more spaces between the particles. That means it looks like a gas phase, low concentration, gas phase. If you are with a low volume with the same number of particles, the intermolecular distance is actually low. That looks like a solid space. So when increasing the volume, you are going from solid to gas. That means when increasing the volume, your entropy will become higher. Entropy will also increase, right? The idea is clear. So when volume increased, entropy will increase. So you can consider solid liquid gas situation there as well. Right? Third stuff. Physical state. The effect of physical state is very clear, no? Right? So when considering entropy, for a solid, it is the minimum. For a liquid, it is a bit higher value than solids, but for a gas, it is the greatest. It's very clear, right? Number 4. Right? POO mixed nature. POO mixed nature. Right? So let's come up with this example. POO mixed nature. Let's come up with this example. Right? Right? You are with a with two gases, let's say, actually which were separated by some wall there, right? Here you have blue color gas molecules, and here you have green color gas molecules, right? Blue color gas molecules and green color gas molecules. Okay, this is black and green, right? So these are pure gases, pure, right? Pure gases. If you are to get rid of this wall at the center of the vessel, these two gases will get mixed like this. Two gases will get mixed like this. It's a mixture, right? Pure nature and the mixed nature. So think of the randomness. Think of the randomness. If you are to pick a ball from here with this space, if you are to pick a ball from this space, definitely it's going to be a black ball. Definitely it is going to be a black ball. But if you are to pick a ball from here, right, it could be a black ball or it could be a green ball, as these molecules are moving here and there. But here, even though these balls are moving here and there, as it's a pure state, definitely it's going to be a black ball. Uncertainty is very less, definite, randomness is less. But here it is so random. It could be black, it could be black or green. It could be black or green. It could be black or green. Randomness is there. Uncertainty is high. Randomness is high. So randomness is high. Here randomness is low. So more the mixed nature, more will be the entropy. Greater randomness, greater will be the entropy, right? So that is the idea. So when mixed nature is high, your entropy is high. Right? The idea is clear. Finally, the amount of matter. Amount of matter. If you are with more gas molecules, greater will be the kinetic energy of the system as the considering temperature. Even all the other factors kept constant, only change in the amount of gas molecules is what we are doing, right? So when you have more gas molecules, more will be the kinetic energy of the system, as kinetic energy is equal to 3 by 2 nRT. 3 by 2 nRT. So when n increases, number of moles of gas molecules increase, right? Your kinetic energy will increase. So more will be the thermal motions of particles in the system, right? So greater will be the entropy. So when amount of matter increases, entropy increases. Right? Let's say when moles increase, entropy increase. So that one can say entropy is an extensive property. Entropy is an extensive property. Depend on the amount of matter. Entropy is an extensive property. Clear? Molar entropy is kind of intensive. All the molar values are intensive, right? But the entropy, the total value, is kind of a extensive property, which depends on the amount of matter. Right now, when amount of matter increases, entropy increases. The idea is clear now? Okay, just complete this note now. Right. Just complete this stuff. Right. Okay. These are the factors within the entropy. Right. Right. Let's move towards the next section. Right. Next thing. Now, actually, entropy, like enthalpy, is also considered as a state function. State function. Right. So, entropy is a state function. So, if you are thinking of a state function, the change of a state function depends only on the initial and final states. Right? Those are the state functions. That is what state function means. Right? So, entropy is a state function. So, change of entropy, that means delta S, depends only on the initial and final states, so that we can apply the equation for the state functions. Right? This thing, delta S is equal to, delta is R, let's say, entropy change of a reaction is equal to summation of entropies of products, final minus initial, final means products in a reaction, minus summation of entropies of reactants. Initial means reactants in a chemical reaction. Right? If you are considering the node things, standard values, these may appear as node values. So, as entropy is kind of a state function, you can apply this equation to solve for delta S not R. Right? Delta R is equal to summation of S naught of products minus S naught of reactants. Products means the final state of a reaction. Reactants means the initial state of a reaction. Right? So, here Lamai, note that these products minus reactants won't come up with delta values. When it comes to enthalpy, the reaction delta H naught R was like delta H naught F of products minus delta H naught of reactants. This is just delta. Delta products minus delta reactants were there when it comes to delta H naught R when it comes to enthalpy change of reaction. But when considering the entropy change of reaction, delta S naught R, we are not supposed to come up with delta here. Right? If you are to write some delta here, you will lose marks. They won't give you marks for that equation there, right? Okay, so just write S naught products minus S naught reactions. There's a reason for that, Lama. There's a reason for that. The reason is entropy is actually coming up as an absolute value. The entropy of chemical species are considered as absolute values, not relative to anything else. Not relative to anything else. Those are absolute values. Right? The provided data for entropy values for any chemical is referred to as absolute values. But the enthalpy values are assigned relative to the reference forms. We consider the heat content in a reference form as 0 for any considering element. The reference form is there. We consider their heat content as 0. Actually, that is not the true case. Those are not 0, as we can't measure that thing, as we find no way to measure that thing. We consider them as 0, the heat content in a reference form. Then relative to that 0, we measure the values when it comes to enthalpy, right? So the enthalpy data given are actually not absolute values. Those are reference to, related to, right, the values of the reference forms, considering reference forms as 0. But when it comes to entropy, those are absolute values, the correct actual values. As we all know that entropy is carrying a 0. Where the entropy 0 situation happens? When the temperature is at Kelvin 0, there will be no thermal motions with particles. Kelvin 0 means you don't have any motions with the particles. T is 0 means kinetic energy is 0. That means no motions with the particles, no thermal motions with the particles. There the entropy is 0. So entropy is with the absolute 0. Entropy is with a 0 value, some absolute value, absolute situation there. So with related to that, so you have an absolute 0, actual 0 there, right? So the entropy values given are actual values, right? Not any value considering some reference state, right? Idea is clear, no? Right, so that no need of applying delta there. It's not a change, just the accurate value as entropy values, right? So if you apply delta there, right, it is considered as false, right? No? Okay, so just write this equation. Delta S naught R is equal to sigma summation of S naught products minus summation of S naught reactants, right? So let's apply this thing to the equation given there. So they have provided this equation, A gas plus 2 of B gas, right, giving you what, C gas and 3 of D gas, no? Right, if you are considering delta S naught R for this thing, right, we can write it as delta S naught R is equal to S naught products minus S naught reactants. No need to write the sigma thing, right? No need of writing the sigma thing always, right? Even without sigma thing you will get marks, right? So S naught products minus S naught reactants, right? Okay, don't write the delta there, don't write the delta here. Here delta appears but not here. If you apply the values there, you come up with the products. You have C gas, so S naught of C gas plus you have 3 of D gases, right? 3 of S naught of D gas minus these two, S naught of A gas plus 2 into S naught of B gas. Right now? So that is going to be the delta S naught R of this reaction. So this, we can apply this kind of equation as entropy is also a state function. For all the state functions, we can apply this. The change of state function depends only on the initial and final states. Right now, just complete this stuff, Lama. But if you are with notes here, all the things should appear with notes, right? That is clear? Right. Shape, no? So let's do some examples. Let's go to the example there. Right. Okay. And this is the example. They have provided you this reaction between the H2 gas and the O2 gas. 2 of H2 gas plus O2 gas producing H2O. This reaction is provided. Right, and first thing they are asking is predict the sign. The sign of delta S naught R. Right, the sign of delta S naught R. The sign of entropy change. Right, for this kind of a question, right, what we are supposed to do is just first see the number of gas molecules appearing at the left hand side as well as the right hand side, at the reactant side as well as at the product side. So here number of gas molecules right here 2 and 1, 3 moles, 3 molecules, 3 molecules, 2 plus 1, here just 2 molecules. Right, you clearly see number of gas molecules, right? So don't you see this thing? Yeah, no. 3 molecules, here 2 molecules, right? So number of gas molecules, that is what we are considering here, right? Right. So we clearly see when the reaction occurs, number of gas molecules is decreased. So you are with 3 gas molecules here means you are with more thermal motions here compared to here. More the amount of gas molecules, more will be the thermal motions of the particles. Right? Gases carrying the greatest thermal motion ability, right? So more gas molecules here, that means here the entropy is high. Less gas molecules here the entropy is less. So going from reactant to products, the entropy decreases. Entropy decreases. So that the reaction carrying some negative delta S naught value. Negative delta S naught value. The idea is clear, right? The points are number of gas molecules increased. Number of gas molecules, molecules decreased. That means entropy increased. Entropy decreased. Entropy decreased from going from reactant products. That means delta S naught R is negative. Right? Is how we are supposed to predict, right? Entropy decrease means delta entropy negative, right? It's like this now. Delta x positive means the property x increases when going from reactant to products. The property x increases when going from reactant to products. Delta x negative means the property x decreases. Negative means decreases going from reactant products. So the opposite is also true, right? If property x increases from going from reactant products, the delta x is positive. If property x decreases when going from reactant products, the delta x is negative. So like that, when property entropy decreases when going from reactant products, the delta property, delta S, is negative. Right now? Okay, the idea is clear. Right, that is how we are supposed to predict the sign of delta S naught R. Secondly, they are giving you some values and ask you to come up with the delta S naught R, right? What are the values they have provided? So substance, right? S values are provided. S values are provided. S naught values are provided, no? See that these values are provided in joules per Kelvin per mole, right? Not the kilojoules, like in enthalpy. These values are given in joules per Kelvin per mole, right? So for H2 gas, O2 gas, as well as for the H2O gas, the things are provided. 130, 205, 188. Normally coming up as positive values. Right? Let's solve for this thing. So you are supposed to come up with the delta S naught R. So we can write delta S naught R is equal to S naught products minus S naught reactants. S naught products minus S naught reactants, no? Right. So let's apply the values there. At the product side, you have 2 of H2O molecules. 2 of H2O molecules. That means 2 into H2O's value, 188. That is the entropy of products. That minus 2 of H2Os, sorry, 2 of H2 gases. So 2 of 130. Plus some O2 is happening, right? That is 205, 1 molecule of that, right? So the unit is joules per Kelvin per mole, right? So let's solve for this thing, right? Let's simplify the values. Right, 2 into 130 and 205, no? Minus 89. The value is minus 89 joules per Kelvin per mole. See, it should be a minus value, should tally with what you have predicted, right? As number of gas molecules decreased, the entropy should decrease. entropy change should be a negative value, right? Okay, so this is how you are supposed to solve this kind of a simple problem. Clear, no? Right. Shape, ne? Okay, just do the working. Right, no? At the next page, Lama, you have given some reactions. They have provided some reactions for you to predict the sign of the deltas. To predict the sign of the deltas, some reactions have been provided. Right, just go through those and see, right, whether you are able to predict the sign of the. Right, just go to this thing at the page number 38. Right. So do the correction with the first one. It should be calcium carbonate solid lemon. With the first question, Roman number 1, it should be calcium carbonate solid. And do this correction and do the stuff. Just do the draft lamai. You're supposed to predict the sign of these reactions for the deltas. This should be solid, right? Right. Let's try to predict the signs of these reactions for delta S naught. This is not R, right? Okay. Right. The first one. See, you don't have any gas molecules at this side, but you have one gas molecules at this side. So number of gas molecules increased when going from reactant to products. So entropy increased. That means delta S naught R is positive. Entropy increased, no? This R is positive. Number of gas molecules here 4. At this side is 2. So number of gas molecules decreased when going from reactant products. That means entropy decreased. That means delta S naught R is negative. Entropy decreased. No? This one. Number of gas molecules 0 here. Here just 4. Number of gas molecules is 4. Here 0. So number of gas molecules increased. That means entropy increased. That means delta S naught R is positive. Entropy increase means entropy change is positive, right? This one, number of gas molecules is 0. Here number of gas molecules is 1, right? So number of gas molecules increased. That means delta S naught R is positive. Entropy increase means entropy change is positive. Number of gas molecules is 0 here, right? Here as well 0. You can't predict with use of gas molecules then go for other ways of considering the entropy changes, right? So just think of the thermal motions of the particles. Just think of the thermal motions of particles. Here it's a solid, so thermal motions are very minimum. Here aqueous solution, that means the particles are moving. Thermal motions are high here. So thermal motions increases going from reactant products. That means entropy increases going from reactant products. That means delta S naught R is positive. Entropy increase means entropy change is positive. This one, number of gas molecules is 3. Number of gas molecules is actually 2. So number of gas molecules decreased from going from reactant products. That means entropy decreased. Entropy decrease means delta R is negative. Entropy decreasing means entropy change is negative. Number of gas molecules here is 1. Here is 0. So number of gas molecules decreased when going from reactant products. So entropy decreased when going from reactant products. That means delta S naught R is negative. Entropy decrease means entropy change is negative. Here, number of gas molecules is actually 2 here. Here as well 2. Number of gas molecules is 2. So number of gas molecules won't change. So we have to think of other factors affecting the entropy. Right, here we can apply the pure and mixed nature. Pure and mixed nature situation, right? This is pure. The starting state, the initial state is a pure state. The final state is a mixture. Final state is a mixture. Starting state is a pure state. Final state is a mixture. So when going from reactant to products, mixed nature increased. Mixed nature increased. So entropy increased. That means delta S naught R is positive. Entropy increase means entropy change is positive. Right now, that is how we are supposed to come up with the signs of delta S for these given reactions. Right now, let's complete the stuff now. Right now, okay. Let's move towards the next section. Right. after predicting the sign of delta S by looking at the reaction, by mainly considering the change in number of gas molecules or with the other factors, right? After that thing is done, right, now we are going to discuss about some other section related to entropy. Right, here what we are focusing on is actually, right, actually we are going to relate the delta H naught value of the system to the delta H naught, to the delta S naught value of the surrounding. So what we are going to discuss here, so we are going to discuss about sign of delta H naught of system and sign of delta S naught of surrounding. This is what we are going to discuss now. These two are related, right? These two are related. Let's discuss how, right? Okay, let's consider this thing, right? So let's consider kind of an exothermic reaction. When an exothermic reaction, right, at the system, right? It's like this now. Consider this is your system, right? You have the exothermic reaction there, right? So that delta H naught system is exothermic, negative, right? So that means my system will release heat to the surrounding, release heat to the surrounding. This is what happens when an exothermic reaction occurs at the system. Let's consider what happens to the surrounding then. As heat is released to the surrounding, the temperature of the surrounding will increase. Temperature of the surrounding will increase. As heat is released to the surrounding, the temperature of the surrounding will increase. That means thermal motions of particles in the surrounding will increase, so that entropy of surrounding will increase. That means entropy change of surrounding is positive. Entropy increases means entropy change is positive. Idea is clear? That is what happens when an exothermic reaction happens at a system. Right? Clear? Let's consider the other way around as well. When an endothermic, right? An endothermic reaction at a system right? Okay, so then system will looks like this, right? You have system here, right? Endothermic means they are a reaction with delta naught positive occurs. Delta naught positive occurs, right? That means heat will be absorbed by the surrounding. Heat of the surrounding will absorbed by the system. That is the idea. So what will happen to the temperature surrounding then? So temperature surrounding will decrease. Temperature surrounding will decrease as heat is absorbed to the system. So thermal motions of particles of the surrounding will decrease there as now less temperature is there. So that entropy of surrounding decreases. That means your entropy change of surrounding is negative. Entropy decreases means entropy change is negative. Clear? Right? So complete this note as well. This is at the page number 38, the bottom part. Just complete the stuff. Right, no? Okay. That is all you should know about the entropy, the concept of entropy. Let's move to the next section. So now we had completed about the study of entropy as well as the enthalpy. Right, so now we can think of the delta G, which gives you the combined effect of entropy and the enthalpy. Right? Okay, so let's come to that parameter, right, which will help you to predict the spontaneity of the reactions. Right? Gibbs free energy. Let's come up with that. Gibbs free energy. Right? G. Right? Okay. So Gibbs free energy gives you the combined effect of enthalpy and entropy, right, which is normally right, considered as the H minus Ts. This is a fundamental equation related to the Gibbs free energy. Right, it will give you the combined effect of enthalpy and the entropy, which will be related with the absolute temperature as well. Right, so this is also a state function. Right, so Gibbs free energy is also a state function. That means the change of Gibbs free energy, that means delta G, will depend only on the initial and final states. Right, so Gibbs free energy is also a state function. So change in G, that means delta G, depends only on the initial and final states. Right, so we can come up with this form for this one as well. What is that form? Delta G is equal to delta G naught F of products minus delta G naught F of reactants. Right, as Gibbs free energy is also a kind of a state function, we can apply this common equation, which is valid for all the state functions for Gibbs free energy as well. So here as well some delta value appears, right, because for G as well you don't have an absolute value, because G is consisted of H as well. For H you don't have absolute value, no. So that means for G as well you don't have an absolute value even at Kelvin 0. Even at Kelvin 0, even though this term disappears, you don't have absolute value for G because this is not coming with absolute value. So delta thing should be applied there. That is clear? Right. So if we are considering a change, right, when a change is considered at same, at let's say as constant temperature and pressure, when a change is considered at constant temperature and pressure, right, we can convert this equation to this form. Delta G, the change is considered at constant temperature and pressure. Let's we write it as T and P. Change in Gibbs free energy at constant temperature and pressure will be equal to the change in enthalpy minus, as the temperature is constant, it is not a change, just T as constant temperature, minus T change in entropy. Right, so this is valid only at constant temperature and constant pressure. Right, constant temperature and constant pressure, remember that. So if the pressure is not constant, we can't think of a delta H, right? The enthalpy changes are measured with constant pressure situations, right? So only as the pressure is constant we can think of delta H. The enthalpy changes are measured only with constant pressures, right? So heat content of a constant pressure process, is referred to as the enthalpy, right? Heat constant content of a constant pressure process. So delta G is considered always when the pressure is constant, and for this equation T should be also constant, right? So you don't have delta T here, some constant T here, right? So this equation converts to this when you are considering a change happens at a constant temperature and pressure, right? No? Okay, so this can be used, the sign of this delta G appearing from this equation, the sign of delta G appearing from this equation can be used to predict whether a reaction will occur or not at this given, at this considering temperature and pressure, right? So by considering this reaction and the sign of this delta G, we can comment whether a reaction will occur or not at the considering temperature and pressure, right? By actually considering the sign of delta G here, right? So let's think of how we are supposed to predict with the sign. It's like this now, right? So first of all, here the T is absolute temperature, right? Keep that in mind as well. Here T is absolute temperature, right? Kelvin temperature, right? Okay, so let's think of the way of predicting whether a reaction will occur or not, whether a reaction is spontaneous or not, with this of sign of the delta G. It's like this, Lamai, right? If the sign of delta G, right? Let's see the signs. Like if delta G, so I write it in black. If delta G, right, is negative, if delta G is negative, then we say the reaction is spontaneous. Reaction is spontaneous. If the sign after applying this equation of delta G gives you a positive value, we say the reaction is non-spontaneous. The reaction is non-spontaneous, right? If the sign equals to 0, if you don't have a sign, that means if the delta G is equal to 0, then we say the reaction or the system is at equilibrium. So if you need some example for equilibrium systems, like when considering the phase changes, the systems are at equilibrium. Phase changes, that is melting, boiling, at the melting point, at the boiling point, the systems are at equilibrium, right? So these things are not that much considered in this lesson, not that much considered in this unit 5, but there is a complete lesson, the unit 12, to study about the equilibrium. To study about the equilibrium, we have a complete lesson, the unit 12, the chemical equilibrium. There I will study about the reactions with delta G equals 0. But with this lesson, mainly we are focusing on these two stuff, delta G minus and delta G positive things, right? Okay, so like this, by considering the sign of the delta G, you can predict whether a reaction will occur or not. If the delta G is negative, that means reaction is spontaneous, that means reaction will occur at the constrained temperature and pressure. If delta G is positive, that means reaction is non-spontaneous, that means reaction is not happening at the constrained temperature and pressure. That is what delta G positive means. Right now, so just write this stuff as well at the space there. Right. Okay. Right. Let's do some predictions. Let's do some predictions using this. Okay. So let's go to the page number 41 there. Let's go to page number 41. Right. See whether we can predict a reaction will occur or not with the use of these theories when the enthalpy change and the entropy change, the signs of them are given. Right. Let's see. Right. Now we are going to predict the occurrence of the reaction when the signs of delta H and delta S are given. Right. So you can say according to signs of delta H and delta S, the sign of delta G decides, or one can say spontaneity of reaction decides. Right. Let's consider this idea. Let's come up with some examples. See what will happen when the delta H is minus and delta S is positive. Right. Delta H is minus and delta S is positive. Right. Okay. Let's apply these signs to our equation and see whether the reaction will be spontaneous or non-spontaneous. We know delta H minus T delta S gives you delta G. Right. So delta H is negative, delta S is positive. So as the delta S is positive, this whole thing is then negative. Now always T is a positive value, right? Kelvin temperature is always positive, right? You don't have negative values for Kelvin temperature. You don't have negative values for the Kelvin temperature, right? Kelvin temperature is always positive, right? So no need to consider the sign of that thing there. Right? Multiplication by a positive value won't change the sign. Right? So that no need to consider that sign. So minus into plus, giving you a minus value. So ultimately what we need to do is some minus plus minus, minus plus minus, minus plus minus gives you a negative value. So delta G is negative. Delta G is negative there. So we can say irrespective of temperature, delta G is negative. delta G is negative. One can say delta G is always negative. Right? It could be a larger value for temperature or it could be a smaller value for temperature. For any value of temperature here, delta G is always negative. Right? So irrespective of temperature, delta G is always negative. That means reaction is always spontaneous. Reaction is always spontaneous. Right now? Okay. Let's think of the second situation. When delta H is positive and delta S is negative. Right? Let's see what happens to reaction then. So we can apply these signs to the equation of delta G. See, so delta H is positive, so delta S is negative. So this whole stuff become positive. Minus into minus is positive. So you are supposed to add some positive value to a positive value. Add some positive value to a positive value. That is going to be, it's going to be positive, right? So if you are considering a smaller temperature or larger temperature, still the sign of this won't change. If you increase the temperature or decreasing, sign of this thing won't change. So sign of delta G also won't change. Right now? Okay. So irrespective of the temperature, delta G is always positive. That means such reactions won't occur even you are to increase or decrease the temperature. So reaction is always non-spontaneous. Reaction is always non-spontaneous. The idea is clear? Right, like this llama, we can predict the sign of delta G when you know the signs of delta H and delta S by applying to the equation. Right? Okay. Right. Let's do the third example as well. What happens when delta H and delta S both are negative? Right? Okay. Let's consider that as well. Right now? Okay. I erase this stuff, right? Right. Number 3. When delta H is negative and delta S also negative. Right? Let's apply these signs to the equation. Delta H minus T delta S is equal to delta G. This is negative. This is also negative. That means this whole stuff is positive. Negative into negative is positive. Now you see, you are supposed to add a negative value and a positive value, negative value plus positive value. So sign will be decided by the larger value, by the larger value. If this negative value is higher than this value, like minus 20 plus 10, like this, so the total value is minus. If this positive value is larger than the negative value, like minus 20 plus 40 plus anything 25 or something, then when the positive value is larger than negative value, the final value is a positive value. If the negative value is larger than the positive value, final value is a negative value. See, the larger value, then the highest magnitude out of these two will decide the sign, right? If negative value is larger than the positive value, the total value is negative. If the positive value is larger than negative value, the total value is positive, right? Okay. So then, whether this value is larger than this or whether this value is smaller than this will be decided by T then, temperature. If temperature is low, this value will be a lower value. This value will be a lower value. The multiplication will be a lower value. So that minus value will win, making the delta G a minus. If this value is a larger value, this multiplication will be a larger value, right? So positive value wins. Then this value, the positive value wins then. It's a large value, so delta G will be a positive value. The sign of delta G will be decided by the temperature then. Right? So we can write there, right? Spontaneity or sign of delta G will be decided by the temperature. Right? So first thing, when temperature is high, what happens? When temperature is high, it's like this, no? Delta H minus T delta S. This is negative, this is also negative, right? When temperature is high, this value is high, positive value is high, so that, right, your delta G will be positive. That means reaction is non-spontaneous. As delta G is positive, reaction is non-spontaneous. Right? So when temperature is low, you can apply those things to the equation again. This minus, this whole stuff is positive then. When temperature is low, this positive value is low. Positive value low means negative value wins. Negative value is high. That means delta G will be negative there. As delta G is negative, the reaction is spontaneous. So you clearly see the spontaneity or sign of delta G will be decided by the temperature. When that is high, the reaction is non-spontaneous. When it is low, the reaction is spontaneous. Whether the reaction will occur or not will be decided by the temperature, right, you are using. At some lower temperatures, the reaction won't occur. Sorry, reactions will occur, but at some higher temperatures, reaction won't occur. Right? That is the idea there, right? Such kind of stuff are appearing, right? Higher temperatures, reaction won't occur, but lower temperatures, reaction would occur, right? That happens when your delta H is negative and delta S is also negative, right? No? Okay, just complete this stuff. Right, no? Okay. Then let's move to the next one. When delta H is positive and delta S is also positive. Let's see what will happen then. Number 4. In both are positive, right? See, so we can come up with the equation here. Delta H minus T delta S equals delta G, right? Delta H is positive. This guy is also positive. That means this whole stuff is negative. Positive into negative is negative. So when this value is greater than this value, delta G will be negative. When this value is smaller than this value, delta G will be positive. This guy is smaller than this value wins. Delta G is going to be positive. So that will depend on the temperature. When the temperature is high, this value will be high. When the temperature is low, this value will be low. Right? The temperature is high, this value will be high, so it will be greater than this one. So that delta G is negative. When the temperature is low, this will be low, then this will be lower than this one. So delta G is going to be positive. Right? The idea is clear. So the spontaneity or the sign of delta G will depend on temperature. Depend on temperature. Right? So when temperature is high, let's apply the stuff again. Both guys are positive. No? When temperature is high, this thing is high. Sorry, this is positive into negative is this thing is negative. Sorry for that. Positive into negative is negative. When temperature is high, your negative value is high, so that delta G becomes negative. So we can say as delta G is negative, we can say reaction is spontaneous. This is what happens at higher temperatures. So let's discuss about what will happen at lower temperatures. When temperature is low, consider here delta H minus T delta S delta G, as both are positive, right? Things should look like this, right? And when the temperature is low, this negative value is low, so you have a greater positive value then, so delta J is become positive. So we can say as delta J is positive, the reaction is non-spontaneous. Right? So if your delta H is positive and delta S is positive, right? So your reaction will be spontaneous at higher temperatures and your reaction will be non-spontaneous at lower temperatures. Just think of some decomposition reactions like calcium carbonate decomposition, right? Such example, if you need an example, calcium carbonate decomposition. Right? Is this thing calcium carbonate solid giving you calcium oxide plus CO2. Right here, endothermic, you need to supply energy to start the reaction, endothermic, and delta S is, see, number of gas molecules 0 here, number of gas molecules 1 here. Number of gas molecules increase means delta S, entropy increases, delta S increase, delta S positive, this is positive, right? Delta H is also positive, endothermic, you need to supply energy to start the process, right? So with these kind of reactions, right, in basically thermal decompositions, if only you are to supply the decomposition temperature or greater than that temperature, the reaction would occur. So only at higher temperatures the reaction would occur, at lower temperatures won't. So best examples are thermal decomposition reactions, right now. That is the fourth situation. So with this stuff, we can think of predicting the sign of delta G, then the predicting the spontaneous and unspontaneous nature of a reaction by merely looking at the signs of delta H and delta S, right? The idea is clear? Right, complete the note there. Right now, හරි. එහෙනම් ළමයි අපි අද අන්තිම section එකට යමු. This is also the last section of today's work, as well as the last section of the theory part of Unit 5. Right? So we'll do a question. We'll do a problem solving using this equation. Right? Using this delta G is equal to delta H minus delta S, right? This thing. We'll do a question, right? That question is appearing at the page number 39, right? Let's do that example question, right? The question at the page number 39. Right. Right, let's do this stuff. So the reaction is this, no? The given reaction is this: CO gas plus half of O2 gas producing the CO2 gas. Right? The Roman number 1. Right? What they are asking is calculate delta G naught value. Right? First question is calculate delta G naught for this reaction at 27 Celsius. Right? That is the first question asking. Then they are asking about the spontaneity of the stuff that can be decided by the sign of the delta G, and finally they are asking some other question as well. Right? Okay. Let's try to solve this one. Calculate the delta G naught for this reaction at 27 Celsius. Right? To calculate the delta G naught, we are supposed to use the delta G naught is equal to delta H naught minus T delta H naught reaction. Right? So to calculate this thing, right, we are supposed to use what? We are supposed to use this reaction, right? Delta G naught is equal to delta H naught minus T delta S naught. We are supposed to use this reaction, right, to calculate this delta G naught. Right? So with the use of this reaction, if you have to solve for delta G naught, first we need to come up with the delta H naught as well as delta S naught. As temperature is okay given as 300 Kelvin, 27 Celsius means 300 Kelvin. But first we need to come up with these two values, right? So let's start with that, solving for delta H naught as well as delta S naught. Right? So first thing is that to come up with delta G naught, right? So first finding delta H naught R. So delta H naught R can be found, right, with the use of delta H naught R is equal to delta H naught F of products minus delta H naught F of reactants, as all the formation values of products and reactants are given. Right? So let's apply this stuff. So as products, the CO2 appears. So the formation value of CO2, that is given as minus 393. Minus 393. The formation value of CO2. Right? Okay. That minus the formation values of reactants. CO is there, O2 is there. The formation value of reactants, the CO. CO coming up as minus 110 kilojoules mole. Only 1 mole is there. And O2, the formation of O2 is 0 as it's a reference form. Right? For the reference forms, the formation values are 0, right? Kilojoules mole, substituting with the correct units. So this value is going to be like minus, this becomes plasma, 282.5. Sorry, this is 5, right? Okay, in kilojoules per mole. Okay. So this is done. Then we need to copy delta S naught as well. Right? Delta S naught as well. So finding delta S naught R. So let's come up with the same kind of reaction, right? As it's a state function, the entropy, you can write it as delta S naught R is equal to S naught products minus S naught reactants. Right now? Don't put any delta there. Don't put any delta there. Right? Entropy is with absolute values. Right? Okay. products. You have the CO2. You have the CO2. So S naught value of CO2 is 213.5 minus the CO is there 197.5 plus O2 is there, so it is 205. Right now, so those are the values, right? So it is joules per Kelvin per mole. Joules per Kelvin per mole. Right now. So let's come up with the value there. And this is divided by 2, right? Sorry, the half of the O2 is appearing, right? Divided by 2. Half of the thing is appearing, right? Half of O2. Right. Let's come up with that value. 213.5 minus 197.5 minus 205 divided by 2 is given as 86.5, right? It's minus 86.5. It is joules per Kelvin per mole. Right now? Now we can combine these two to here to come up with the delta G naught. Right now? Okay. Let's copy that. Finding out delta G naught R. Right? So we can apply the equation. Delta G naught R is equal to, so I'll write it here now. So right, so delta G naught R is equal to delta H naught R minus T delta S naught R. Right? No need of writing this R thing, right? R leave when I get out right. Okay. If you can write the R, no worries, right? Yeah, okay. So delta H naught R, that is minus 282.5 kilojoules mole minus T is 300, this means in Kelvin 300 Kelvin temperature is needed, into delta S, that is 86.5, and this is in joules per Kelvin mole, but we need to substitute in kilojoules mole, right? Because kilojoules mole is needed, right? So when it comes to units and dimensions of this thing should be equal to dimensions of the other term, right? Okay. So let's come up with kilojoules mole, right? So to come up with the kilojoules, we need to multiply this thing with 10 to the power minus 3 kilojoules, right? Per Kelvin per mole. Per Kelvin per mole. Right now? So we can simplify this stuff, right? So you have this thing. Let's simplify this stuff, right? So it is like 0.3 now. So you have minus here, no? Sorry. Minus become plus, right? this value becomes plus 25.95, that thing minus this, right? (256.55) minus 256.55 in kilojoules mole. That is the delta G value which we were looking at, right? Okay. So that is the value there, right now. Okay, the Roman number 2. The Roman number 2 question, what they are asking? What they are asking is predict whether the reaction is spontaneous or not. Right? Predict whether the reaction is spontaneous or not. As delta G is negative, we can say this reaction is spontaneous, right? That is how we write the comment there. As delta G not is negative, reaction is spontaneous. As delta G not is negative, the reaction is spontaneous. Right now. Problem number 3. What they are asking. At what temperature reaction starts to occur spontaneously? At what temperature reaction starts to occur spontaneously? That is what they are asking. At what temperature reaction starts to occur spontaneously? Right. So it's like this, Lama. So if you are considering delta G, right, gives energy change, the thing would be like this. You have the 0 here, you have the negative values here, you have the positive values here. So if the delta G is negative, the reaction is spontaneous. If the reaction, if the delta G is positive, reaction is non-spontaneous. Right? So reaction starts to occur spontaneously actually at 0. When delta G is equal to 0. Right? This is where the delta G is equal to 0. This is where the reaction starts to occur spontaneously. Right? When delta G is positive, reaction is non-spontaneous. When going from positive value to coming towards the negative value, that first occurrence of reaction spontaneously happens at delta G is equal to 0. That is the boundary. So for this kind of question, when the reaction starts to occur spontaneously, or for a question like when the reaction starts to occur non-spontaneous, or when the reaction stops occurring, for such kind of situation, right, you have to consider the delta G is equal to 0 situation, right? So for this special point, delta G is equal to 0. So we can apply that thing, right? When reaction start to occur spontaneously, delta G is equal to 0. So you can apply the values, right? So we can say delta H minus T delta S is equal to 0. So if you are subject T, so T is equal to delta H divided by delta S, right now? So we can substitute these values, right? The delta H value is this, minus 282.5 kilojoules per mole, and delta S value is what? Minus 86.5. In kilojoules mole, it should be multiplied by 10 to the power minus 3 kilojoules per Kelvin per mole. Unit should be tallied, right? Kilojoules per Kelvin per mole, kilojoules per, right? So that will give you the temperature value in Kelvin, right? See this stuff. So 282.5 divided by 86.5. So and multiply by 10 to the power 3 will give you 3265. 3265 Kelvin value. So that is where the reaction starts to occur spontaneously at Kelvin 3265. So that is this value, right? Okay, the idea is clear. So that is the answer to the Roman number 3. Right? Okay. That's it. That's all for this lesson. But you can complete this stuff, right? That is all for unit 5. And from today, we are winding up the lesson, right? So let's meet with the question sessions, the past paper question settings, right? On Friday nights. Goodbye then. See you next week.